Yeah, hi and welcome back everyone to chapter 3, Coding Attention Mechanisms. So this is a supplementary coding along video for the Build a Large Language Model from Scratch book. And here I'm trying to walk you through some of the code examples to explain what attention mechanisms are and what role they play in the large language model. This is actually a very technical chapter, maybe the most technical chapter in the book, because it's similar to implementing the engine of a car, where the engine is the most complex and the most technical aspect of a car, in my opinion. So, but it's also a very important topic because it helps us really understand what the LLM is doing and why LLMs are, let's say, different than other types of models. For instance, the transformer architecture introduced this self-attention mechanism that we are going to code in this chapter, and it's been very transformational in terms of developing these large language models. And also in the grand scheme of things, just to take a step back here, what we are trying to do here in this video, or in general what I'm trying to do with the book, is to help you understand how large language models work. We are going to build a large language model in the next chapter actually, and then we are going to train it in chapter 5, but we are still, keeping things more self-contained and small. For educational purposes, this will be a fully functional large language model. However, it's more on the smaller scale compared to, let's say, the latest ChatGPT models. So personally, how I would see it or compare it is that we are here implementing an LLM that is more similar to an old Ford Mustang, for example, from the 1960s. It's a real car, it drives. However, it's not the latest and greatest car. It's not like a Ferrari, which has been engineered with millions, if not billions of dollars, a lot of expensive machinery. So this would be a car, I would say, that is impossible to build by a single person. You need a big a team for that, or a team of highly professional experts, and you need also a lot of high precision machinery, where with this old Ford Mustang you might know that it is possible actually to maybe not build the whole car, but to restore it and to fix it by yourself. So if you're interested in cars. And so in that sense, the LLM we are building here, it's not a high performance car, it's more like a simpler car that we can work on ourselves. However, it still helps us understand how cars work if we're building this simpler car. And the reason why we're doing this is we can do it by ourselves without having to spend millions of dollars on, let's say, GPU compute to train a large scale model. However, anyways, the methods we are going to introduce here are the same. So there's lots we can learn here. And in particular, we're going to start here with section 3.3, attending to different parts of the input with self-attention, where self-attention is a mechanism to parse the input data. So for instance, if I go to the chapter itself, just to show you where we are in the grand scheme of things of this book or this video series here. So in the first chapter, we talked a bit about setting up our Python coding environment. And then in chapter 2, we talked about the data preparation and sampling. So here we downloaded text data and we formatted the text data, we tokenized it, and we set up the PyTorch data loaders. And we are going to use those later when we are training the LLM. Now we are implementing this attention mechanism, one of the core parts of the LLM. And then later on in the next chapter, we will be implementing the LLM architecture. So if I go further to chapter 3, I'm already in chapter 3. If I go further to this figure here, this is an outline of the topics we are going to cover in chapter 3. So they are all centered around the self-attention mechanism. However, we are going to approach this step by step. First, we are going to start with a simplified version of self-attention, just to highlight the big picture concept. Then we are moving from the simplified self-attention to the real self-attention mechanism. And then we are going to add on specific things that are used currently in the decoder LLMs, the popular types of LLMs, and that is causal self-attention. So this is the concept of causal self-attention, and then we are going to take it one step further and implement multi-head attention, which is essentially a more advanced version of causal attention. But we will see exactly what that means later on. Right now in this section, in section 3.3, we are going to be focused on this simplified self-attention to introduce the concept of self-attention gently. So the reason why we are actually developing self-attention, or why we care about it, is to address a shortcoming that other types of neural networks had. So I don't want to go over all the details here. If you're interested, you can maybe read the chapter in its entirety. But the main idea here is that previous types of architectures, for example, recurrent neural networks, when they translated from one sequence to another sequence, for instance, here this would be German to English translation, what they had to do is they had to memorize state of the input. So they were reading the whole input, and then before they could generate the output, they had to kind of save a summary, or like a latent representation, a condensed representation of the input, and then using that input step by step generating the output. If you are not familiar with recurrent neural networks, don't worry about it. It's not really important for the remainder of this chapter or this book at all. It's just I'm mentioning it here for, I would say, completeness for those who are familiar with RNNs. Now, what's important though is that here the shortcoming is when you translate text from one language to the other, and you can't really look at the full input sentence. You can only have like this intermediate state. You might lose information, and then it leads to an unoptimal or suboptimal translation. So the idea in self-attention is for each step when we generate text, so whether we translate text or whether we answer questions, we get information from a text, or we do anything with text really, where we generate text, at any time we can look at the whole input. So that's the core idea of self-attention. So for instance, if we have a translation task and we are translating the next token, so this is a German sentence, and this would translate into "can you help me?" So if we're here, we generated the first output. Now we are here translating the second output. At each step, even though we are at the second output, it cannot only look at the previously generated token, it can also look at all the other input tokens. So it has access, so there's a mechanism to access all the input tokens that we have provided as the user. And what's more important even is that we give it selective access. So for example, in this case, when this sentence is translated into English, it's looking at all the input sentences, but I try to visualize it here with these dots. Each input token has a different importance. For example, this first word has a medium importance, and these two words have a very small importance, very small dots here, where this token has a relatively high importance because it's relatively important for translating this particular token. So if you know German, du is the German word for you. So in this case, this is actually a very important word for translating this word. And so here we are assigning a higher weight. We make this token more important. And in a similar case, the LLM is doing this automatically. So it's assigning these important weights to the different inputs. And these important weight or importance weights are the so-called attention scores. And we are going to compute the attention scores, and sometimes also called attention weights. But there's actually a small distinction between attention scores and weights that we will get to later on also in this video. So the short story here is that when we are generating text at any time, we can reference the whole input text. If you, as a user, you ask a question, give me the five most important facts of my input document, the LLM at any time when it generates text, it can reference the whole input without having to store an intermediate representation. So it's actually a very powerful mechanism. And so in the grand scheme of things, so what we are going to do now is we are going to implement this self-attention mechanism. Before, in the previous chapter 2, video or videos, we covered the pre-processing steps. Now we are assuming we have already processed our data, and we are jumping directly into this self-attention module. And then later on in the next chapter, we will be implementing all the other parts that go into LLM. So one more figure before I go to the code examples. Here is a summary of what we're trying to accomplish with the self-attention mechanism. I mentioned this referencing of all the input, but on a more like zoomed in level, what we're trying to accomplish is we are going to transform the inputs into a different type of representation. So in chapter 1, what we did is we took an input text, for example, your journey starts ... step. Let's say this is an input sentence that I truncated a bit here for brevity so we can fit it onto a figure. So if we have an input text like this, remember from the previous chapter, we are tokenizing this, and then we are converting the token IDs into so-called vector embeddings, so embedding vectors. And each vector here, just for simplicity, has only 3 values. So we talked about this more in the previous chapter 2 videos. So where we have a vector representation. And now here, what I'm showing you is the vector representations of all the inputs. What we are going to do now is we are going to consider one of these inputs that we want to transform into a so-called context vector. It's called context vector because this Z here, it's also an embedding vector, but it has the information of all the inputs. And so this is, if I scroll up a bit, it is kind of connected to what I told you earlier here. So when we are generating this output token, so this specific token, it has information about all the input tokens. It's actually a weighted sum over all the input tokens. So you can see that this one is more important, but all of them are involved in generating this one here. And so when I scroll down again, this is what you can see here. We have all the inputs here, and they're all involved in generating this output vector here. They have different importances though. So here, these alpha values, alpha to 1, to 2, to 3, and to t, they are all different weights, and this is a measure of how much of this input vector will be represented in here. So it's maybe a very mathematical concept. It's a linear algebra concept in a sense, because we're going to compute a dot product here. But you can, maybe we will see in the code, maybe it will be more intuitive once we look actually at the code. But so this is the big picture level. We also, one more thing I should say is we are going to focus on the second input. So here, x2. So x2 is the focus here. And this will give us the context vector with respect to this input. All the inputs play a role here, but you have a specific set of alpha weights. So you can see there's always a 2 in here. 2, 1, 2, 2, 2, 3, and 2t. So this means this is the weight of the first input with respect to this one. And this is the weight of the second input with respect to the second input. That's why it's 2, 2. And then it's the weight of the third input, 3, with respect to the second one, and so forth. So this context vector is specific to this second one here. Why it's the second one? It's just because I chose it for this example. Ultimately, we are going to do it for all of them. So if I go up one more time, here I also picked the second one, and the second one looks at all the input tokens. But this is also true if we look at the first one. It would similarly also look at all the input tokens, or the third one, and so forth. We just have to pick one now for the example, because otherwise, if we start picking multiple ones, it gets too complicated. We will get to that later, because ultimately we do this computation. So we do this computation here for all the vectors, but to keep it simple, we are going to focus on x2 as the reference. And the reference is also often called the query. So let me actually go to the code, and then we can actually look at this in a more concrete way, where it's maybe a little bit less abstract, and maybe this helps with understanding what is actually happening here. So let me copy a tensor here I have. So we are going to use TensorFlow again. And so This is the complete sentence similar to the figures I showed you. So your journey starts with one step. This is my input tensor, and each row here is the embedding vector corresponding to this token. So I'm, for simplicity, assuming each word is a token, but it could be a bit different. It could be split into two tokens depending on how a tokenizer works. And yeah, tokenizers was a topic in chapter 2. For simplicity, we are just assuming each token is one word, and then we have this three-dimensional input vector embedding for each of these words. So going back to the figures one more time. So here, I'm showing you, so here this is, if I go up one more time, sorry. Here, this is the complete, let's say, procedure. We are going from inputs to this context vector, and we have these intermediate weights. But we don't know yet how to compute those. So we will take it step by step. So we are going to break this down into smaller steps that get us to this context vector. So the first step we are going to take is we are going to compute these intermediate values. So before these alpha values, I don't want to scroll up again, but the alpha values, they are the so-called attention weights. Before we compute the attention weights, we compute the so-called attention scores, which are an non-normalized or unnormalized version of the attention weights. The attention weights will come later. This is more like one step towards these attention weights. How they are computed is by computing a dot product between an input and each value here in this sequence. Again, like I mentioned before, we are taking example 2, x2, as our query. And then for this query, we are comparing it to each of the inputs here. And so one thing, again, I want to highlight is we are talking about a simple self-attention mechanism. Later on, we will talk about the real self-attention mechanism, but to keep things, I would say, step by step and at least making it a bit more approachable, I wanted to start with a simpler version because we can always make it more complicated later on, but I think this nicely highlights like the idea behind it. So how we compute these values is by taking the dot product between the two. And in linear algebra, the dot product, it gives us a sense of similarity. It's a measure of how similar two vectors are, essentially. I mean, there are things involved like taking the vector norm, normalizing the vectors, length normalization, and so forth. But for simplicity, we're not doing that. We are just computing the dot product, and you can think of it as a way to measure the similarity between two vectors. So if I scroll down, let me just go to the code notebook. It might be easier. So we have now this input tensor here. And so this input tensor contains 1, 2, 3, 4, 5, 6. We're going to focus on one at a time. So let's consider as our input vector, well, let's call this the input query. We are considering, let's say, this one. So I can also reference this as inputs. Or let's take the second one because that's what we had in the figure, right? If you recall, here we have x2. So we are going to also use x2 here. And x2 would correspond to the second row because Python is indexed 1. So x2 would be the second row. 0, 1. Yeah. Okay, so this is our input query. We can print it out. There we go. This is our input query. And we do the same thing now considering a different vector. Let's just choose the first one here. So let's call this input, let's say 0. Or input 1, because then we are consistent with this number. It's maybe more intuitive. And so we are going to call this inputs 0. Input 1. So this is the vector we have here. Now, what we're going to do now is a manual approach. So we're going to compute something here that is taking the element-wise, we are multiplying the vectors element-wise. So if I do just, brute force by hand, just to illustrate it, we multiply the first value with a second value here. Then this value times this value plus this value times this value. And so we get this value out here. So this is essentially this vector dot producted with this one. And there is a nicer way to do this in PyTorch. We can do actually torch dot and then take this one and this one, and we get the same value, as you can see. So this is a so-called dot product. That's what we're doing here. And now, we could do this actually for all the different inputs here. We only did it for the first one, but it would be a lot of work, right? So we have to either write it like this or this for each one. So what we could do is we could actually write a for loop. So if we do a PyTorch, or let's do a Python for loop first. If I do a Python for loop, just copied it here. So what we can do is we can say for each element in my inputs value, we have a result here, and we are going to add them to it. So it's essentially what I've been doing here. So for each element, so if I print it out, for element in inputs 0, let's do like print element. So it's for each element here, right? And then we have index, which is a different way of accessing this. So this should not change if I do it like this. Oops, iterated over 1D tensor. Oh, I forgot an enumerate, I think. So IDX is just a position. So this is the same, still the same here. You can see we are just iterating over it. But why I'm using the index here is that I can now do the same thing for the query. So we have this input query, right? So I can now also index this one. So let me change it so it's nicer. Or let's just leave it like it is. So here I can now multiply those two. And then let me just print them. So I have these, and then I can actually sum them. So one way would be, let's do starting with 0, and then let's just add them up. So we're adding them up. And then let's double check result. So you can see what I've been doing here is the same that I've been doing here, but now I can do it for all the different vectors, right? So I can go through those. Actually, 1 second. I should probably use a variable here. Otherwise, we will get always the same results. Let's do I and I, so that we can change the vector here. So the vector 1, 2, 3, 4, 5, 6, and so forth. So this is the first one. That should be the same that we got before. Then we can do the same thing with the next one, another one, and so forth. But again, this is still a lot of work, right? So one way to make this actually easier is to use the dot products, right? So I could technically go in here and do, then I don't need that one. Then I could do this. So we don't need this also then, just making it more efficient. So I can do inputs I and input query like this. So we don't need this one, but see, it doesn't change. So it's the same as before. We are just replacing this manual summation with this dot product. And if I do the 0, it should give me this one or this one, basically. So this is one way we can automate this. Now, going one step further, this code here, what it does is it's doing the same thing, except now we are going to do it for all of them all at once. Instead of me having to change this here like this all the time, we are going to have a for loop that does that. So for each input xi, so the I here, for each I in this collection of inputs, we are going to compute the dot product with the query. So we call that input query, right? And we're going to store them in this output tensor, because it's one. So in PyTorch, in Python, we could use a list and append to a list, but in PyTorch we have vectors and tensors, and they have a fixed size. So it is possible to extend those, but it's very inefficient. Usually tensors are a fixed size, so we have to, for efficiency, say how big our tensor should be. And so here we are saying it has the shape 6, because that's how many rows we have. 1, 2, 3, 4, 5, 6. So that's what we're doing here. We are instantiating this, and then we are filling in the values that we got here. So if I print this, you can see these values here are the same I'm getting here. So if I have a 2, 0, 1, 2, so this is this value here, right? And so if I want to get 0, 1, 2, 3, this value, this is the same as putting a 3 here. You can see these are the same. So all we have done now is we have made this a bit more convenient. We use this torch dot method instead of us doing this for loop manually and filling in the values. So going back, and by the way, I was a bit, I skimmed over this, but I think there is a typo here. So you can see these are the same values. This should be actually correct in the PDF version, because I'm 100% sure that this was fixed, or I fixed this. So I have to contact the Manning layout team to also update this here in this website version. And so if you're a bit confused why these are the same, they shouldn't be the same. So they should actually be different values. Pretty sure in the print version it's correct, and I will just contact the Manning team to also update it here. Anyway, so we have implemented this now. So we have these values. So these values here are the values you are seeing here. And for visual purposes, I truncated them. So 0.9 really refers to 0.95, and then 1.4 corresponds to 1.4 here. So instead of rounding them, I truncated them, because then I thought it's easier to identify them here, because otherwise it would be 1.5, and then you would be looking here and where's the 1.5 here, right? So that's basically why why these numbers are different. They were a bit too large or too long to have them here in the figure, so I just truncated them. Okay, so we have done this step now. We have these scores. Now the next step would be going from the scores to the attention weights. And again, the whole reason why we are doing that is it's a measure of similarity. How similar is the input to this query? So if I look at these values here, or maybe it's easier to look at them here, you can see this is a higher value than this one. So 1.4 is higher than 0.9. So one might say, oh, journey, here the second word journey is more similar to the input, which happens to be also journey. So it's a way of saying, oh, they're more relevant to each other than this one, which is a bit different. Now, these values later on, there are weight values involved. So here we are talking about attention weights, but there are parameter weights, like neural network weights, that are going to be trained in chapter 5. And then these scores are optimized for the task at hand. So sometimes, depending on the input, one word is more important than the other, and the network will learn how to recognize which word is important with its weight training, basically. So here, it's a very simple attention mechanism, like I mentioned before. So I wouldn't take these values too seriously. It's more for highlighting what is the actual computation that is happening in the attention mechanism. So what we have done so far is we took the dot product between an input and each of the other inputs. We got these scores. Now we are going to normalize these scores so that they sum up to 1. So it's a normalization, and this is done so that we don't get crazy large numbers, and it helps also with the optimization process to have smaller numbers. It's more like a cosmetic thing to do. And so there are different ways we can normalize. So you probably would think of the most intuitive way of dividing each score by the sum, right? So that would be one way to do it. So if I have, let's say, attention weights let's call this temporary because we are going to introduce another method later. So attention scores 2. And then what we could do, we can just divide this by the sum. And yeah, probably you already know what happens now. This will be then giving you the normalized scores. You can see that, and they are all smaller than 1, but what's more important is, of course, that they now sum up to 1. So just making the properties a bit nicer for normalization purposes. And there's one actually more common way of doing that. It's the so-called softmax function. So I'm going to define the softmax function here myself, and this is something I wouldn't use in practice because it's not very stable numerically for certain values. But just to illustrate it, it's basically the exponential of the input divided by the exponential value, and then similarly the sum. So this is similar to what we've done here. So this will also give us normalized values. So we call that, let's do it like this, call that attention scores 2. So the reason why I'm calling this attention scores 2 is that it is with respect to the query for the second input token. So that's why the 2. We would technically do that for all the other ones too, but we would have to change the query. And that is something we are going to do in the next video. So, or the next section. So, but yeah, sticking with our normalization here. So here we have, again, a normalized tensor. The values are slightly different, not that much different. You can see it's roughly the same. If you would round them, you could probably get very similar values here. But it has slightly nicer properties during optimization when we are training the neural network. So it's again just a small tweak to get better optimization when we are training the network. And so yeah, this is how we normalize the weights, how we get from here to here. Now there's one more thing I mentioned. This is a simple softmax version, so it might not be ideal. Certain values might be unstable. So I highly recommend actually in practice, if you're doing this, to use the PyTorch version of that. So softmax, and then let's do this. Oops. Yeah, my mouse keeps sliding off my desk because it's at an angle. I'm sorry. But so yeah, here what we are doing is we are just using the PyTorch version. So in this case, you can see that the values are exactly the same, but there are certain values where this one will fail or be unstable, and this one is a more optimized, stable version. So whenever there is a PyTorch function that is already implemented, it is highly recommended to use that one over self-implementation. However, self-implementations are always nice for understanding how things work. So you can, by looking at this mathematically, understand what's happening, because with this one, it's a bit more abstracted. So it's harder to understand how this works. So what we have done now is we computed those scores. And there's one more thing in this section I want to do, and that is computing the context vector. So if you don't mind, let me scroll up one more time. So I promised I would not do that, but it's maybe the last time for this section. So in the beginning, we talked about taking the inputs, computing the attention weights. This is all what we have already done. And then we compute this context vector. So we have this, the inputs, we have the attention weights, but we don't have the context vector yet. And that is what I'm doing now. So what we are going to do is we are going to use those as weights to compute the weighted sum over these inputs. To make this a bit more clear, I think I have a nicer figure here somewhere. here. So we have the inputs again, and then for each input, we multiply it with this attention weight for each one separately, and then we just sum up all these vectors, and then we get that context vector. And again, the idea is of this context vector that it combines the information from all the input vectors, in a sense that those with a higher attention weight, they play a larger role in the output. So in this output vector here, the weighted sum. So weighted sum you can also think almost as averaging, but with a weight where each one has a different importance. Okay, let's actually do that. So I have some code I will put in here just so that it is a bit quicker, because I realize it's a very long section. So what we are going to do here, we are going to initialize them with zeros. So we have a empty vector. Let me show this. So we have 3 values, and that is the desired size of our context vector. If I go here again, we want 3 output values, and it's the same shape as the input. We have 3 inputs, and we want 3 outputs. Now, what we're going to do is, so we have the query, again, is our second query, which is why we call that the second context vector, like vec2. Because later on in the next section, we're going to do this for all the other vectors. Right now, we are still laser focused on Z2, the computation with respect to the second input token. So the second input token to all the other inputs. And by the way, that's also why it's called self-attention. So that is, we are considering one of the input, and then we compute the attention to itself, to the whole sequence, to each input there. Okay, so we have the second input as the query. We have these zeros, just initial values. And then we are going to iterate over all the vectors in the input. So maybe let me show this. Print xi. Oops. Of course. Yeah. So, and these, if I go up here, these are those. So looking at them, they will look familiar to you. So we are just iterating over all these rows, one row at a time. And then we multiply them with our attention weights. And again, I'm using this trick where we have the index position. So we are indexing. So maybe I can print it out here to make it more clear. So we have index 0, 1, 2, and I could actually get this value by doing this. The same thing. Now, we use this index so that we can also access the weights. So the weights are those here. So before maybe I do this, let me comment this out, and this is maybe easier to see. So we will have x1. Let's do it like this. Print attention weight. Oops. Yeah, there we go. Yeah, I have my keyboard at a slightly different angle for the recording, which is making typing a bit more unintuitive for me. Okay, so yeah, so we are just looking at the attention weight and then the associated vector. We can also change this to make it more intuitive to this. There is an error here. Oh yeah. Attention weights is not defined. Did I not? Ah, I see. I should have saved those. Still not defined. Well, this happens when you, oh yeah, there we go. Okay. Okay, so we have this first attention weight. We multiply it with this first vector. We have the second attention weight. We multiply it with a second vector and so forth. And this is what is happening here. So make this a bit more intuitive. So we have this multiplication here. This one with this one, this one with this one. And then we are adding them up. So should do it like this. So this is plus equal, which means we're adding it on top of this one. So it's a weighted sum because we are weighting it. We're weighting the input with this attention weight, and then we are adding it all up on top of each other. So the result, let me comment this out. So the result is this one here. And this is the context vector. So this is the context vector that we are seeing here. Again, the truncation 0.4, 0.6, and 0.5. So 0.4, 0.6, and 0.5. And so what we have done now, I realized it was very technical, so I encourage you to maybe step through this a bit more slowly by yourself. But yeah, what we have done now is we computed this context vector with respect to the second input element. In the next video, I will show you how we can do that for all the other ones. So, because it is a lot of work if we would have to repeat this, because you have to compute the attention weights. So what we would have to do is we would have to change the query. For example, if we want the first input token, we have to change it to this one here. And then we would have to change it here and here. And then we have to also compute those in the first place. So we have to go back, change this one, and so forth. So it would be a lot of work. So in the next video, I'm going to show you how we can generalize that to all the other inputs.
Get this book at Manning.com